Yeah, indeed. So my name is Allard Oelen. Maybe I will not repeat then the title of the presentation since you already did so. So my co-authors Marcus Stocker and Zern Auer, and I'm a PhD student from the Technical University or Technical Information Library in Hanover. This does not seem to work. Yes, that seems better. Okay, so maybe a quick outline of my presentation first. I'd like to introduce a bit of scholarly communication and what the current problems are with that. Afterwards, I will discuss a little bit more about our approach, and then finally a brief evaluation and conclusion. So currently, scholarly documents are mainly communicated in a narrative document-based form. So this also applies to the knowledge presented within those documents. So you can see here on the left, PDF is the most commonly used format to do this. But of course, the downside here is that machines cannot easily process this knowledge. So it's not really machine actionable. As a result, if as a researcher, I have a very specific information need, so in this case, I'm looking for research related to author name disambiguation using graph embeddings. And if I use a tool like Google Scholar to find this, you will see I get over 18,000 results. And many of them, of course, are not relevant. If we were using knowledge graphs instead to publish the knowledge instead of these documents, we could retrieve the information really more effectively. So here we have a simple example of a paper and a graph structure. So this paper addresses a certain problem. It has an approach, and there is some metadata related to the paper. If now I want to find papers that address this research problem, so author name disambiguation, with this specific approach, then I can easily get all the papers that address these problems from the graph. So it's really a more narrow search that we're looking at then. And that's exactly what we're trying to do in the ORKG, the Open Research Knowledge Graph. So we're trying to build a knowledge graph of science. So not only of scientific metadata, but also really of the knowledge coming from these articles. Yeah, in order to do this, of course, we need to somehow transform the unstructured knowledge to structured knowledge, so to extract that knowledge from the papers. And broadly speaking, there are two approaches here. We could go the automatic way and the manual way. So automatically, we can, for example, use NLP tools to extract the knowledge from the papers. Of course, that approach scales quite well, so we can process many papers. But yeah, the current state of the art is not accurate enough to generate a high quality knowledge graph. On the other hand, we have the manual approach, for example, using crowdsourcing. So we could use the crowds to transform these papers, but of course, scaling here is a problem. So the more papers you want to transform, the more people you need to do this process. But on the other hand, compared to the automatic approach, most likely it's more accurate. So what we're proposing instead is to use a combination of the two. So we want to intertwine NLP with microtask crowdsourcing. And that's what our approach is about and what I will be discussing next. So we want to apply NLP, so a set of NLP tools on large quantities of scholarly articles, and then form a knowledge graph from that. So that's the machine intelligence part. Then we want to have humans that validate the knowledge using microtasks, so the human intelligence part. So here you have a brief overview of how that looks like. In dark blue here, we can see such a microtask where we ask a user whether the statement is correct, yes or no. And on the right, you see the possibility to vote. So yes, no, or I don't know. And you have a very brief overview of how this works. So we have scholarly abstracts on the left. We process them, build a knowledge graph, and then show the triples in this microtask here. And then the votes are fed back to the knowledge graph and stored as provenance data on the statements. So maybe a little bit more in depth here. So we have a 6-step approach to extract the knowledge, generate the knowledge graph, and validate the knowledge. So in this specific case, we used archive and their metadata corpus. And we then use the abstract and the titles of those papers to process them with 5 different NLP tools, which in total address 4 different NLP tasks. So we have entity recognition, entity linking, topic modeling, and summarization. And the summarization is really related to the last presentation, to this too long didn't read summarization. So a 1-sentence summary of an article. Then we store this information in a document storage. We, in a later step, semantify this, so build triples from that, and then finally ingest it in a knowledge graph, in this case, GraphDB. And then we have the microtasks, so have users vote on the correctness of the statements. To do this efficiently and also in a correct manner, we create question templates for the microtasks. So each specific NLP task here has an own template. So the first one, the entity recognition, is a bit more open information extraction. So we have 2 different tools for that. And the question looked like this. It's really a statement question, so whether the subject predicate object is correct. For the second one, the entity linking, we use Ambifirst NLU. And there you can see the question is the term something related to, and then a link term in Wikidata. And then the user can hover over the link to Wikidata to see the definition from Wikidata, but also hover over the term to see where it's coming from in the abstract, so you can see the position there. Now we have the topic modeling done using the CSO classifier, the computer science ontology classifier, and we ask whether a paper is related to a topic. And then finally the summarization, asking whether a sentence does indeed summarize the paper correctly. So this is how it looks like integrated in the Open Research Knowledge Graph. So on the top, we have the metadata of the paper. Then underneath, you can see the voting widget. So this is where users can see a statement and vote on it. And under that, we have the list of statements. So next to a statement, you can see a score, which is indicating the correctness. And also the tooltip shown above is basically showing users how the score is calculated. So you have the user votes combined with the assistant's confidence score, and this is then an aggregated score of the correctness of the statement. And we have the provenance data showing an excerpt of the abstract, including some information about the tool that generated this statement, and the version and the creation dates. And then finally, we have something, trend analysis. So that's more a use case of the data. So you can, for example, see how often a tool or a term is used over time. So you can see the years. Now it's not visible, but underneath you can see the years, and you can see that this term is getting more popular over time. So I briefly want to mention something about provenance data, because that's one of the crucial points here. So we, of course, need to store all this information in the graph. So not only the statements, but also the tool that generated it and the votes from the users. So on the left, we can see the metadata of the paper, the title, the abstracts. Then here on the right top, we have the NLP generated data. And for one of those statements underneath, so CSO object recognition, you can also see the provenance data. So the tool that generated the statement, including the reference in the text or in the abstract, so where it's coming from, and we can see 1 vote and how it's recorded. So it's attributed to a certain user there. And this is all stored using an RDF star syntax. So very briefly, finally, some results in the conclusion. So it's late-breaking work, so we didn't really have a full-blown evaluation yet, but we wanted to mainly evaluate our technical infrastructure, whether this is feasible with this amount of triples and how long it takes to process the information. So in total, we processed about 95,000 articles coming from archive, as I said, and that's approximately 5% of the whole corpus. And we selected all the papers that were classified as machine learning. So in total, we have around 65 million triples there. So that includes the metadata, the provenance. As you can see, a relatively large share of that amount is provenance data, and on average, a little less than 700 statements per article. Then possibly interesting as well, the processing time per NLP tool for this size of articles. So we run this on a server with only CPUs, with 40 cores and 300 gigs of RAM. And here you see an estimation of how long it takes. So the longest is the entity linking of a little less than 40 hours. So one thing to mention, we didn't run the summarizer on all the abstracts because we only use the CPUs and no GPUs here. Yeah, so finally, some of the conclusions. So we presented TinyGenius to validate NLP statements, scholarly NLP statements using microtasks. And basically the important thing here and our objective was that we can now have, instead of just content consumers to our platform, to the ORKG, we try to transform them into content creators. So people that would just come to consume information, to read a paper, they are now actively asked to contribute to the ORKG. They don't need an account to do so, they can just vote, and it should make it a lot easier there. The short evaluation showed that the infrastructure and the technologies used, they are suitable for the task. And then next we have some future work where we want to implement this in the live system we have. I want to do evaluations based on the generated data. And also we want to work a bit more on data consumption use cases. So, okay, now we have this knowledge graph with all these terms in there and all these papers that are described. What can you do with this and how is this helpful for a regular researcher? That's it from my side. Thank you for your attention, and I'm happy to take questions.